Okay, here we're going to look at a very special case, and that is a reversible steady state flow process. So we've got the flow through a control volume, and it's internally reversible. And specifically, we're actually going to just look at a single inlet, single exit control volume. Okay, so for the heat transfer, you'll remember when we first were introducing entropy at the beginning of this chapter, we said that the heat transfer for an internally reversible process is TDS, right, which is temperature times the change in entropy. Okay, and that's a relationship we got second law from that and things of that nature, right? Hopefully you also remember that we know that TDS, we developed those TDS equations. We know that TDS equals DH minus VDP. Okay, so hopefully you remember those two concepts. Okay, plugging those in, putting them together, I get basically that my heat transfer now is the change in enthalpy minus the integral of VDP. Okay, now I'm going to take that and plug it into my first law equation to find the work. So this is the first law equation solved for work. So that is the heat transfer plus change in enthalpy, kinetic energy, potential energy, right? Now I'm going to plug in what I just put in here, or what I just developed for the heat transfer, and what happens is my enthalpies all go away, and all I'm left with now is the integral of VDP and then the kinetic and potential energy. Okay, so this is the equation for a single inlet, single outlet, reversible steady state flow process. Very specific case that develops the work for that. Now, here's the one that we actually are going to use moving forward. When we have an incompressible substance, i.e. a liquid, like water going through a pump, okay, and I need to know the work of said pump, of a liquid going through that pump. Okay, and again, as per usual, when we neglect the kinetic and potential energy effects, okay, the work of that incompressible substance going through this steady state reversible flow process is that volume, right? And the volume doesn't change for an incompressible substance. So the volume times the change in pressure. Now, again, this one's boxed in. There's lots of equations that you'll see, but this is the important one. This is the one that we'll actually be using in our development when we get into vapor power cycles, where we're actually dealing with pumps. And the work of a reversible pump is the volume, which does not change, of a liquid going through a pump times the change in pressure. Okay, but again, that comes from the equation above, which is the integral of VDP, kinetic and potential energy, right? Neglecting kinetic and potential energy, having a constant V, I'm left with this equation. And this is really the equation that we use moving forward. However, the other equations still do apply if you need to find work of a reversible steady state flow process. Okay, now, we also can, from here, develop for polytropic processes, right? We have these relationships. We have the development for work for polytropic processes of a closed system. Now we're going to do it for a control volume, okay? So we'll start with any substance where the work now, again, ignoring potential and kinetic energy effects, is the integral of VDP, or the negative integral of VDP. Again, PV to the n equals constant. Therefore, V actually equals the constant over P all up to the 1 over n. So I can pull the constant to the 1 over n out, and I'm left with 1 over P to the 1 over n in the integral. Performing that integral, again, depending on if n is 1 or not 1, I get different responses. And here's the equation for that. I'll let you do the calculus on your own if you want to. Otherwise, you just know if I have a polytropic steady state reversible process, I can use this equation to figure out the work of that process. Again, the boxed-in equation over there is the one we're going to be using most often here. Okay, but again, if you know you have a polytropic steady state reversible process, you can find the work using these relationships, knowing pressure and volume of the states. Okay. For an ideal gas, basically employing the ideal gas model, basically getting temperature involved here, we get these relationships here. And these are very close to the relationships we had for a closed system, just a little bit different because instead of PdV, now I have VdP because of the control volume idea here. Okay. The other relationships that relate P, V, and T, those are still the same as they were before. It's just the work equations are a little bit different because the work of a steady state reversible process is, again, VdP rather than PdV, which it was for a closed system. Okay, now, whole lot of stuff here. To be honest with you, I boxed in the one equation that you're going to use the vast majority of the time out of any equation on here. And again, we're going to use this a lot when we get into vapor power cycles and start discussing the work of a pump, which is an incompressible liquid reversible process.